Okay, welcome back. Let's continue the last track, the track 4, which is situated interactive multimodal conversational AI. And let's welcome the track organizer for the track 4 overview.
Awesome. Thanks a lot, Vivian. This is Satwik. I think we also have Shane and Paul amongst us. We, along with Ahmad, we co-organize this workshop. Shane will take over for the track overview video. Shane, please go ahead. Thank you.
Yep, thank you. Can you hear me?
Yes.
Yes. Oh, awesome. Yeah. Hi again. My name is Shane Moon, and again, today Satwik, Paul, and I will present the summary of our track results. First of all, I'd like to thank everyone who has participated in this challenge, working on this important problem, and also pushing the state-of-the-art in this area together. And so before we present the main track summary, I will briefly go through the problem space for studying and the data sets that we have provided to the participants. So why are we studying the situated and interactive multimodal conversations? In the recent past, we've been seeing an increasing number of usage of virtual assistants, and for these assistants to become an even more integral part of our daily lives, we believe that they need to go beyond just having a conversation in language, but also be able to handle multimodal inputs such as vision and audio, and also perform multimodal actions. So consider this scenario shown here, where the user is in a fashion store, a virtual fashion store, and for a user query, which of these trousers go best with my wardrobe, the assistant should be able to understand the multimodal context that the user is in, and identify the trousers, recollect the user's wardrobe, and eventually respond with a recommendation. I recommend the brown one in the middle. And the assistant should be able to carry the conversation further and respond to additional user queries. For example, can you check its price online, please, and so on. So we proposed the SIMMC challenge as a step towards building these multimodal virtual assistants. And a little more details on how we collected the data set. So SIMMC consists of natural language dialogues that are grounding in co-observed and evolving multimodal context. So for this challenge, we collected task-oriented dialogues capturing many different conversational aspects around the shopping experience specifically. Our data collection interface was based on the prior work, Crook and Kottur et al., that pairs two human workers in a live chat and assign them the roles of a user and an assistant, where the role of the user is to browse through a catalog and purchase items, while that of the assistant would be to facilitate shopping experience for the user. So both of these, the user and the assistant playing agents, co-observe the same multimodal context in the form of either a virtual environment like the one shown here, or a set of images. And during the conversation, the assistant can manipulate these co-observed contexts depending on the need of the conversation by, for example, either by populating the carousel or interacting with the items or providing additional information and so on, and therefore evolving the context as the dialogue progresses. So this video shows our data in action, which assumes that a user is in a furniture shopping scenario. So in our setup, assistant can respond to user requests and present new situated multimodal contexts that are co-observed by both the user and the assistant. And so this allows for rich and complex multimodal interactions within a dialogue. So we provide the fine-grained annotations such as dialogue acts and slots and attributes. And most importantly, as you're seeing here, the multimodal co-references. So in this specific case, the phrase, the brown one, color in purple, and the pronoun it, both have the same canonical reference to an object in the scene, which are all annotating our data set throughout the dialogue. So as you can see, as the conversation goes on, the conversation of multimodal context carries over to the next turns in the dialogue, which makes this challenge more challenging. So overall, we collected a total about $13,000 with 169,000 utterances. And we collected dialogues in 2 shopping domains, furniture and fashion. And for the furniture set, we used the VR scenes as multimodal context, whereas for fashion, we used real world images. And specifically for our new SIMMC data sets, we proposed a new flexible ontology that captures the detailed multimodal interactions within dialogue flows to allow for more systemic study of the multimodal dialogues. And specifically, our ontology uses a hierarchical intent structure where the dialogue act describes a linguistically inspired high-level goal of an utterance, such as to inform or to request and so on, following the popular literature in the task-oriented dialogue that we're all studying. And on an activity that describes more fine-grained intent, such as to prefer, to rotate, and so on, that are specific to the scenarios that we're studying in SIMMC. And lastly, we also introduced a concept called object, which is used to ground and map the multimodal context into this labeling language and a set of attributes that describes those objects and intents. So here's an example. Again, this specific design of our ontology allows for grounding multimodal context together, where in an annotation like this example, an object there, say the blue one here, will refer to both what's described in text and what's also present in the multimodal context, which can be nicely represented as a subgraph here. So we provided all these annotations to the participants, and these dialogue annotations were collected after the dialogue was collected with the help of the professional linguist from our end. So in total, our data set saw 42 different unique intent nodes and 100 different slot types, with total more than 1,600 unique values for those slots. And here are a bit of statistics in our data sets. It does show, specifically this is showing the SIMMC furniture data set, which has an average length of 7.6 turns on average, and each utterance was had about 11 to 12 tokens on average. And we had a similar trends for the fashion side of the data sets as well. So with that, Satwik will continue and describe in details the baseline models for the main tasks we proposed.
Awesome. Thank you, Shane. Can you folks hear me?
Yes.
Perfect. Yeah, thanks for that, Shane. We'll now jump into the details about the challenge itself. Before we jump in, let's look at the challenges that exist in SIMMC dialogues more carefully. Right. So, yeah, next. Right. So at each turn, the assistant, in order to give a response, needs to follow the following reasoning steps. First one is understand the user utterance along with the dialogue and multimodal context. Next, it needs to sorry. So maybe you can undo. You can continue with all the next, it needs to identify and execute the multimodal actions that are necessary. For instance, in this case, if the user requested a view of the back of the chair, and then have to identify and execute that corresponding multimodal action, and then finally respond with a natural language utterance. Next slide. Awesome. And responding with natural language utterance, of course, should also take into account all the multimodal co-references and the dialogue state that exists. So it needs to keep track. It needs to track that as well. So what we do here is we characterize the challenge and the corresponding tasks and provide the evaluation metrics. We'll take a look at them more in detail in the next few slides. Okay, so first we have the history, which is HT, the history of the conversation. Then we have the multimodal state, which is MT, and then the current user utterance at the current round UT. The goal of the assistant right now would be to first predict the dialog state, which we're gonna tag as task 3, where we need to predict the exact dialog state that has been captured in the dialog so far. Next. And next, the next step would be to predict the right assistant API so that we have the right set of actions that, and we can get the right set of information that is requested by the user. And finally, we have the final task, which is the assistant response generation, where we'll have to respond with the natural language utterance. So we label them as task 1, task 2, and task 3, as you can see here. We'll go into details in the next few slides. Next slide, Shane. Thank you. For the subtask 1, which is the assistant API call prediction, the idea is to predict the assistant call, assistant action as an API call, given the dialog and the multimodal context. For example, if we were to search for a particular kind of furniture, we'll need to invoke the API search furniture with the arguments of the corresponding API. In this case, the arguments could be a furniture type of kitchen islands and with a color specification of white. The metrics that we use are the action accuracy itself. And because accuracy doesn't necessarily account for the existence of multiple valid actions, we use perplexity, which is defined as the exponential of the mean log likelihood of the particular action as an additional metric. In addition to both accuracy and also perplexity, we use attribute accuracy to measure how well the model is able to predict the arguments for the corresponding action. Here are the examples. Here are some examples of the APIs that are part of the SIMMC furniture and fashion, respectively. I'll just go through one or two of them. First one being search furniture, where you want to search for the furniture using the specific attributes. Specify info is trying to get information about the furniture based on the attributes and so on. The second subtask is the response prediction, where we want to examine the relevance of the assistant response in the current term. We have two evaluations here. One is a generation problem, where we envision the system to be a conditional language model and measure the closeness between the generated utterance and the ground truth utterance using blue 4 score. The second is the retrieval problem, where in addition to the user utterance, the dialog context, and the multimodal context, we give the model a pool of 100 candidates, which are randomly chosen, unique to each turn, and then see how well the model is able to retrieve the ground truth response from that particular pool of candidates. For metrics, we use mean reciprocal rank, mean rank, and recall at K. And the final and third subtask is the dialog state tracking, where we want to systematically track the dialog acts and associated slot pairs across multiple turns. As Shane was mentioning earlier, we developed a flexible ontology to represent the state of the multimodal context, and we will use it for our evaluation. The metrics in this case would be the intent and slot prediction metrics like F1 score, which is in line with the prior work that in prior work in DSTC, sorry. Now I'll quickly go over the baseline architecture. We build baselines for the first and the second task, which is action prediction and response generation, and build a separate baseline for third task, which is dialog state tracking. For the first two tasks, we start off by an utterance and use history encoder, where we take UT and HT, which correspond to the current utterance and the history, and encode it. Next. We then have a multimodal fusion model where we encode the state of the multimodal context. For example, in furniture, it could be the state of the carousel, where you have information about what objects exist in what positions. And while fusing, we attend to this multimodal information using the history and user encoder. And finally, we feed it into an action predictor to give us the predicted action 80. Next. Take the output of the action predictor and the multimodal fusion component, and then feed it again finally into the response generator to give us the assistant response 80, capital 80. For the user and history encoder, we experiment with 4 different kinds of encoders from prior work, which is a history agnostic encoder, which is a simple language model. We have the hierarchical recurrent encoder, memory network based encoder, and also transformer history agnostic based variation. Here we have the empirical evaluation for these models. At a high level, important trends here are that trends are that hierarchical recurrent encoder and the history agnostic encoder seems to perform reasonably well in the action accuracy prediction, and the simple Chor version, which is the last row, works well for the attribute accuracy and the blue score. And we observe similar trends for SIMMC for fashion as well. Here's the baseline architecture for the third task, which is multimodal dialogue state tracking. For this particular subtask, we use a pre-trained GPT-2 model and first flatten out the dialogue context, which is H of t and U of t together, and also flatten the multimodal context as shown here, where we list a set of objects and as a dictionary of attributes and attribute values, and then feed it into the model. And we let the model predict the belief state, which is DT, and also system response as an auxiliary task. We observe that we achieve a slot accuracy of about 52.5 when we use a text-only model, and 63.9 when we use a multimodal variation of it for furniture. And the trends are similar for fashion, where using multimodal information definitely helps the dialogue state tracking problem. All right, next I'll hand over the floor to Paul to talk about the outcomes of the challenge.
Hi, so hopefully you can hear me. So we had a total of 47 registered participants on the Google DSTC form. We had a number of stars and forks on GitHub, so people were definitely interested in the challenge. In the end, we received a total of 11 entries, which roughly about 13 different models from 5 teams across the world. If the next slide. So to determine which winner is for each of the subtask categories, we listed the metrics gave the metrics in a priority order, and then used those metrics. We looked at the first metrics in each subtask to see if there was a clear winner, where a clear winner had to be at least one standard error different with any other candidate's performance. Where there were more than one candidate, we then used the next metric in our list of priorities. We'll kind of look more closely. Yeah, next slide. It's cool. Yeah. So we had this whole like entries in one standard error becomes important in subtask 1. So our first we evaluated teams in terms of the action accuracy, which is like how accurate were they on selecting the action, and then the second priority on that one was attribute accuracy. Team 2 actually scored the highest in terms of action accuracy, achieving 82.5%. But within one standard error of them was Team 4. And if we considered the second attribute, the second metric, they were much better in terms of the attribute accuracy. So they became the overall winners for that track. Yeah, so subtask 1, we saw an overall increase through the contributions of Team 2 and Team 4 in terms of a 3-point increase in action accuracy. So this indicates our baseline was fairly strong to start with, but then attribute accuracy, there was quite a big jump of nearly 10 points. If we look at subtask 2, again, we see that there's 2 teams in the running here. Actually, those 2 teams being teams 1, 2, 3, 4, 3 and 4. Team 3 scoring higher on the blue score, and we split this task into and awarded it in terms of like who scored highest on the blue score and versus who scored highest on recall. And team 4 again wins again, taking it on recall. And then if we look at the third of the subtask, which was the dialogue state tracking, we see that that team 3 here actually won over team 4 in terms of the dialogue state tracking, the multimodal dialogue state tracking. So for each of these areas, we kind of like had a, if we can look at the winning approaches, I mean, both teams 3 and teams 4 used pre-trained language models. The winner of subtask, essentially, the winner of team 4 of the subtask 1, 2A, and 3 used a BART-based, BART large model. And this also performed very well on the this performed very well across a range of the tasks. If we go to the next slide. So in terms of response retrieval, they were also the BART-based models, but the team actually submitted a slightly different model here, where they used the weights that they'd learned in terms of the response and action selection tasks, and then adapted that BART model to actually do a retrieval task. And that was accounted for their big jump compared to the other teams here, in that they actually specifically trained their model to on the retrieval task, whereas what the other teams largely did was actually do a generation step and then do a mapping from the generation step to select the things in the ranking. So the big boost here came from the ranking. Next, thank you. So the team 3 model, as I mentioned already, was an ensemble of GPT-2 models, and this performed well in terms of kind of the achieving the best overall blue score, but it also performed highly and won subtask 3. And so that we can kind of conclude from here that like large these pre-trained language models, plus the fact that they were only trained using simple language model losses, actually can deal quite reasonably well with this multimodal context. If we kind of look a little bit more into the error analysis, so overall, it's focusing on action prediction. We noticed that certain actions were a lot more easier to predict than other actions. For example, predicting add to cart and specifying info, pretty much all the teams did very well. Search for versus refined actions versus none. These actually turned out to be quite hard for the teams to predict. And we believe that this is kind of because sometimes it's actually not obvious when you need to search for something versus do nothing in terms of the action space, which is the action space is specifically affecting the multimodal space, and then just asking a refinement question to the user, which is not a, so I guess we should say clearly here that actions affect the multimodal space versus there are dialogue acts which are directed towards the user, which are separate from these actions. And next, we also were interested in like what actions were predicted all correct by all of the teams versus what actions were predicted correctly by none of the teams. And we looked at a breakdown of these, and we see again that specifying info, which is basically doing a search into the catalog, was done very well by all of the teams, whereas the selection of the action none, which is do nothing to the multimodal context, was actually an action with which all of the teams struggled. We saw similar trends in fashion as well. The previous slide was for furniture. Again, the models were able to correctly predict, specify info with a high degree of accuracy, but found that predicting none, like that was like one of the cases where it was very difficult for, if we looked across the range of all the teams, there were quite a large number of cases where none was not correctly predicted by any of the models. Looking at response generation, so we used BLU4, to measure the distance between the ground truth and the responses predicted by the various team models. We observed that the BLU score decreases as the length of the generated utterance increases. So this suggests that the information that's being captured in the responses is somehow getting further away from the ground truth. It's not telling us necessarily whether the model's doing bad or not, but they're showing greater variation from what the original ground truth utterances were. We also observed poor scoring on utterances which are fairly short, less than 4 tokens. Part of this is due to unfortunate smoothing in the way the BLU4 metric is computed, but inspecting it, the handful of these examples, we also noted that in many of these cases, these short utterances are mentioning information from the catalog that kind of underlies the shopping domains. And many of the models were incorrectly capturing the catalog information in their responses. Again, we also look again at the BLU score associated with each action. So this is like, given that the system selected this action, what was the accompanying response like, and was there any kind of relation there? And we see that the higher scores tend to be associated with actions that have a limited set of responses. So, and this is maybe obvious. So if you search for a furniture item, or you navigate to a new section of the catalog and show that to the user, then simple bland responses like "how about these" would be more popular or more frequent. And so we see that is likely what is going on here. The difference in the performance of add to cart in furniture and fashion can be explained by the fact that there's actually a lot more instances in the training data of add to cart in the fashion data than there was in the furniture data. So error analysis on the multimodal state tracking. So this is an example of what the multimodal state tracking looked like in the challenge. So essentially, we're trying to track information on like what object is being mentioned, as well as what the intent and other attribute information which is associated with the intent. So overall, we saw that the across the teams, that intent prediction was actually fairly robust. And so most teams were actually very good at the intent prediction and achieved similar levels. Slot prediction was the thing that varied the most and actually tended to separate the teams. And then if we looked into slot prediction, so slot prediction in this case is predicting attribute slots, which are things the user has mentioned, and object slots, which are things that are appearing in the multimodal context. We find that the object slots are being tracked reasonably well, but the attribute slots, which are the things the user is mentioning about items, so color, type of word, or design of dress, are being tracked worst. And we also looked at how the tracking accuracy fared as the number of turns along the number of turns. And we see that there's a general degradation going on here with the models performing worse as the number of turns increase. And even the best performing models from, say, Team 3 doesn't alleviate this, that the models are degrading as time goes on. So this indicates that there's a clear gap in the state tracking accuracy. So our takeaways from having run this challenge. So pre-trained, one of our key takeaways is that pre-trained language models should definitely show promise in this multimodal setting, and that simple strategies like flattening the multimodal context into a stringified form similar to Soloist or SimpleTod, and then using pre-trained language models such as GPT-2 or BART are flexible enough to actually adapt to these multimodal dialogue tasks. However, although we see gains, and we saw gains in our baselines from providing the multimodal context, the fact that we see effects like degradation as the number of turns fall off suggests that the multimodal context is not being fully utilized. So there's clearly a bunch of improvement that could be made on these models. And then a final observation, and this kind of keys into the kind of a database grounding work that has been mentioned in a number of these challenges. We saw that these models are powerful enough to avoid returning safe and bland responses, but they fail to reliably integrate catalog information. None of the team's models actively interrogate the catalog. They essentially relied on the fact that there's a smaller number of items mentioned in the catalog than there are a total number of dialogues to train on. So you're talking hundreds of items in our catalog versus thousands of dialogues. And they're implicitly trying to learn the catalog from those conversations. And we see a lot of errors occurring in the responses due to that approach. And clearly, actually integrating with the catalog, integrating these models with the catalog information, not only would make it more robust, but also would make it more robust to changes in the catalog information. So that's kind of our summary of this track, and we'd be happy to take any questions or any other comments. Thank you.
Can I ask questions?
Yeah, please.
Okay, so you mentioned about multimodal, but actually the information is just tabular representation of the product features. Is it right? Not recognition anything about the products. Nobody wants to answer? Paul.
So what we have the underlying, so in one case, furniture, we have underlying virtual reality scene, which is a fairly simple scene consisting of 1 or 3 items displayed in a virtual reality environment, and manipulations can be made on those items. To avoid having compounding errors through, say, computer vision, we decided that what we would provide to the participants is essentially a textual summary of what is in the scene. So the information that's provided is such as there is prefab item on the left, another item in the middle, another item on the right. And then separately, we provide the catalog information. You can take that prefab ID and go and look up the catalog information, which has a long text description and a bunch of more semantically labeled fields such as color, type, so on. And so the multimodal information that we're providing, and we do similar for fashion. Fashion is based on images. So the multimodal information that's being provided, we're essentially already saying we're assuming that it's already segmented, and we're providing you information about what items have been segmented out of the scene.
So it means that unstructured text representation, including multimodal features, are given to
both structured and unstructured. So you're provided with structured information left item, right item, center item, and then you're provided with a link to more structured information, color, material, style, room, intended room, and then you'll provide, and then also a general text description. So you have a mixture of structured and unstructured information, including the information about the scene that the user is seeing in front of them right now.
So actually that is dialogue act and slot values, and in this multimodal dialogue means that this new information related to the actually color and shape, this type of information is new, and actually the difficulty comes from that the new slot value and the new dialogue act for the multimodal information. Is that the reason why people cannot handle?
So you have others, please feel to chime in, but you have the information that's coming from the user in terms of an utterance or history of utterances, and then you have the information that's captured in the scene. And so you're trying to combine these two sources of information. Rather than having a single history, you have essentially two streams of information.
Thank you.
Right, and I think another big challenge here is that the multimodal contexts are updated throughout the dialogue, and there are more items that are introduced throughout the dialogues, and a user can be talking about any of the items that were mentioned, not just the ones that's currently visible to the user, but the items that were mentioned before and so on. So carrying over that multimodal context throughout the dialogue, I think was the biggest challenge that participants try to address.
So actually, you guys have a kind of state transitions complexity figures or something. So perplexity can tell us how complex the dialogue is, but we would like to see how complexity in the dialogues. When I worked in a WFSD based dialogue system, I can show that complexity based on the state. So can you show that one so we can see that, okay, so hotel reservation task is this complexity. And if we add the multimodal information for shopping dialogue, that complexity is much higher or almost comparable. So right now, I'm not sure that if you guys give the exact information of the multimodal features, and that is text-based information, and the complexity is really difficulty, or just training data is not enough to train. So that is not clear yet. So hope you guys can show that complexity of the dialogue with multimodal information and without multimodal information. Okay, thank you very much.
Yeah, thank you. We have one more question. I think in the interest of time, maybe you can just limit to one question. Yeah, please go ahead.
Yes. So I just wanted to confirm that the dialogues that's collected in this data set, it's not like goal oriented. It's just people browsing through the catalog. They might select a furniture to check out, and they might not. So is that like the context of the dialogue?
So our data set was collected in two different settings. One, the goal-oriented data set where the user was specifically given a specific item that they have to buy eventually, and the rest of the dialogues were simulated to satisfy that dialogue goal. And other half of the dialogues were, especially for furniture, were collected in a more like a free form where people were just allowed to browse through the dialogues. And then pretending to have some kind of intent to be interested in a specific set of dialogues. But we did not have those as part of the task prediction per se. But the task-oriented nature of the conversations were still in our data set. And that was the part of the challenge for the DS dialogue state tracking tasks.
Thanks. Makes sense.
Awesome. Thank you. I think in the interest of time, we'll move ahead with some of the other oral talks by the entries that we have here. The first talk would be by Huang, Chor, Seng, Yan Bing Eng, Vishni, Kheng Huiyo, Ridong Jiang, and Jung Jim. It's going to be on joint.
Hello, I will be sharing this slide on my, okay.
Okay, awesome. And then it will be on joint generation and Bi-Encoder for situated interactive multimodal conversations.
Hello, could you see my slide?
Yes.
Okay, so it's a nice talk from Shane and Paul. I will be presenting our works on the joint generation and Bi-Encoder for situated interactive multimodal conversations. This is a joint work of me and my colleagues, including Chen Shen, Yanbing, Wei Shi, Ken Hui, Ridong, and Jiang at Institute for Infocom Research and Institute of High Performance Computing from A-star research entities. As Shane and Paul already talked about the overview of the subtasks for SIMMC. This is just a short introduction of the overview of different subtasks. The first subtask is basically to predict the assistant API with associated arguments given the dialogue history, multimodal context, and the current user utterance. And for the second subtask, there are two types of subtasks. The first one is to generate the system response, and the second one is to select the best response from a list of 100 candidates. The third subtask is to do the dialogue state tracking, which is to predict the multimodal belief states, including the dialogue action labels and attributes at each turn of the conversation. So these are two examples of the fashion and furniture data set. As you can see, for the first example, the user is the user is checking whether a small crew neck splatter is available. For the second example, the user is asking for a light-colored island. So here are the gold action and dialogue state tracking, and as well as the system response from the data sets. So there are 5 baselines models for SIMMC as Sean and Paul already described. The first 4 baselines, including historic agnostic encoder, hierarchy recurring encoder, memory network encoder, and transformer-based historical historic agnostic encoder, which is used for subtask 1 and subtask 3. They are not pre-trained models. And also the baseline model includes a pre-trained GPT-2 model for action prediction and dialogue state tracking. So what we found is there are some limitations on the baseline methods. So first of all, for the baseline methods, each subtask requires training a separate model, and therefore could not capture the semantic relationships between the different outputs. So as you can see for this example, the user is asking for a light-colored island. Sorry. The user is checking whether the user is trying to checking trying to get some suggestions for this color of the island. Also, the system response for the action is to search the furniture, and for the dialog state tracking, the result of the gold answer is to refine the furniture color to be the light color, and the system response is that is to provide the light colored islands we have in stocks. So as we can see for this example, that there are some semantic relations between different outputs of the subtasks. So if we can doing the joint generation of these three target outputs, it's possible that if we predict the correct action or the correct dialog state tracking results, we might get we might get a better system response in terms of generation of the system utterance. Also, another weakness of the baseline model is that it lacks some pre-trained weights for some baseline methods. So as we can see for multiple tracks of the DSTC9, that the pre-trained models definitely help with the overall performance. Also, we can try more variations of the transformer models, which can be adapted to the dataset. So to address these issues, we try to do the joint generation of subtask 1 to subtask 3. Also, we try to use a pre-trained model. Also, we try different combinations of the different transformers in order to do the joint generation of different subtasks. So the idea is we take we consider each subtask as a language generation task. So the task is that given the dialog history HT, multimodal context MT, and the current user utterance UT, and we trying to jointly predict the system API action ACT and the associated arguments ACT arg, as well as the system response R. Also, we need to predict a list of belief state actions I1 to IN, because there are multiple belief state actions for each turn of the conversation. Also, we need to predict the for each belief state action, we need to predict the associated belief state slot pairs. So for the source input string, we basically concatenate the dialog history with the user utterance, as well as the multimodal context, because currently we only use the text description of the multimodal context. So so we concatenate these informations as a single string. For the target output, as you can see, we just concatenate the action with arguments of the action labels and the intent belief states with the arguments of the with the belief state store key value pairs with the belief state. Also, we contact. Also, it is followed by a response, system response. So we consider all these tokens as a single stream. Also, we add two special tokens, the SEP1 and SEP2, to separate the output of different subtasks. Also, we actually we have tried another version, which is to, because for the action and the arguments and also the belief state actions and the slot key value pairs, we also consider them as special tokens. But in reality, we find that it's actually performing, I think, 1 to 2% lower than the treating them as a normal text. I think this is because there are some semantic meaning for these belief state actions or the API action labels. For example, like search database. So you can see if we treat this action label as a special token, we may lose the semantic meaning of this action label, so it might reduce the performance. So the first thing we try is to adapt the multimodal transformer networks into the SIMMC dataset. The MTM model is proven to be effective for the multimodal dialogue multimodal dialogues. So, but for the SIMMC, because we only use the text description of the multimodal context, so here we do not have the video encoder as well as the audio encoder. So we basically feed the dialogue history into the dialogue history encoder of the MTN, and also we feed the user utterance into the query encoder. Here we actually tried two variants of the MTN. The first one is we concatenate the dialogue history with the multimodal context, just like what we did, what we're trying to do the joint prediction of the different subtasks of SIMMC. We concatenate the dialogue history with the multimodal context, and then feed into the dialogue history encoder so that the model can understand the multimodal context. Also, we tried another version, which is to feed the multimodal context into the one of the encoder here. We just use a caption encoder because there is some attention between the caption and the history. So by encoding the multimodal context separately, we might understand multimodal context a little bit easier. But in reality, we find out the performance is actually the same. So this is very interesting to know. Another models we try to do the joint prediction is that we tried different pairs of transformer-based sequence-to-sequence model. We tried 4 models to be more precisely. The first one we tried is bird to bird. The second one is bird to share. the third one is a BERT to GPT-2, and the final one is a BERT to distill GPT-2. Because I think the baseline models already tried the pre-trained GPT-2, so I didn't try to just use GPT-2. Instead, we try BERT-to-BERT approach. The BERT model we use consists of 12 layers, 12 attention heads, and hidden size is 768. For the BERT to share, the encoder and the decoder actually share the same weights. They can still encoder and decoder, they use the same weights. They can still generate the target output. For the GPT-2 model, we use normally a normal GPT-2 model, which consists of 12 layers, 12 attention heads. Also, the hidden size is 768. For the distillized GPT-2, it consists of 6 layers, 12 attention heads, and the hidden size is also 768. Finally, we tried the BART model. So the encoder and the decoder are from the BART model, but the loss we trying to fine-tune is calculated based on the errors of the next token prediction task. So we are not trying to mask the original utterance and trying to recover the original utterance. So we just trying to predict the target output based on the input stream. So we tried both the pre-trained bar base and bar large for the experiments. So here's a formal introduction of our models. So basically, to summarize, we have a source text encoder and a target text decoder. So encoder can be any transformer-based encoder. So the XI is a source input stream. So by encoding the XI, we can get the hidden space of the source representations. Also, we during the training process, we will also feed the target string into the decoder. Decoder can be any autoregressive transformer-based decoder like GPT-2 BERT or BART. The decoder was a BART. Another essential thing is we have to do the cross attention between the hidden representation of the source string and the hidden representation of the target string. So this attention layer output is used to proceed the decoding process. And finally, we use linear layer for language modeling after the last layer of the decoder to get the probabilities of the next token. So we use coarse entropy loss to fine-tune the model. So this is the same structure used in the traditional transformer architecture, which is from the attention is all you need. So here are our results for the joint generation of subtask 1 to subtask 3. So the evaluation matrix including the accuracy of action and attributes, action perplexity for subtask 1, blue 4 for subtask 2, and the intent and slot F1 for subtask 3. So as we can see, all our models perform much better than the baseline models, especially the but large model shows the best results across the fashion and furniture data sets. For the bird-to-bird model, I think it's still very close to the BART model. But in terms of attribute accuracy, I think BART model shows a little bit better than the bird-to-bird model. As we can see from the, especially in the furniture data set, the BART model actually shows 6% higher than bird-to-bird in terms of attribute accuracy. Also for the blue 4, the BART model also shows the best results. So here are our results on the test standard set. So as you can see, our BART large model perform well in the fashion domain. But for the intent F1 and the blue 4, it's slightly lower than the team 3. For the furniture data set, I think we are still doing good in terms of all the subtasks, but for like subtask 1 and subtask 2, we are showing a little bit lower than the team 2 and the team 3. But as you can see for this result, that I think our models overall shows a very stable across different domains. For example, like team 1, they scored well for the attribute accuracy in terms of subtask 1, but it's showing a lower result in terms of other subtasks. So I think overall, the BART large model showing stable results for different subtasks across different domains. So we also measure the accuracy by we also measure the performance of our models compared to the individual training for each subtask. So we can see that the joint learning method is actually performing better than individual training for different subtasks. So the way we did is for individual training, we trained exclusively for each subtask, and we're trying to predict the target output of each subtask. But as we can see, especially for the attribute accuracy, you can see that the joint learning method is performing better than the individual learning method. So also we conducted error analysis for our models in the fashion domain. So as Shen and Paul already did some analysis showing that for the non-action tokens, actually it has a top percentage of error. So the model often confuses the non-action with search database or specify info actions. So we think if we can, for this non-actionables, because it actually, for the model, I think it's very hard, even for human, it's very hard to differentiate the non-action token with other actions. So if there are more categories of the action labels, it may help, I think it will improve the overall performance. Also for the,
I think we are at time. So if you can wrap up in the next few.
Okay.
Yeah, thank you.
I will quickly wrap up. So for the response retrieval, we adapt the Bi-Encoder and the cross encoder for this SIMMC challenge. So the experiments we did was to use a pre-trained BERT and BART from the Hugging Face. Also, we trying to fine-tune the models on the joint generation tasks. So here are our results for the response retrieval. As you can see, our models perform much better than the baseline models. Also, it's showing the best results across different teams. So for the error analysis, I think there are mostly two types of errors. The first one, as you can see, for the ground truth response, have a great day. It may predict your welcome, have a wonderful day. So we think these multiple similar responses can be all considered as correct. Also, there are another type which may require us to look up into some specific information about the product. So this may, for example, the dialogue history is this skirt retails for $11. Also, the user utterance ask about the custom rating. The gold response actually is it's a exact custom rating of 1.44. So so for our predicted response, without looking at some external knowledge, it's not able to predict the exact custom rating of these conversations. So I think we later need to incorporate other knowledge or database of the data sets. So as a to summarize the talk, so we basically developed an end-to-end encoder-decoder model based on the pre-trained BART, which jointly generates the outputs of the three tasks. Also, it achieves the first place in subtask 1 and second place for subtask 2 response generation and the subtask 3. We also see that the joint prediction models perform better than individual learning in different subtasks. Also, we developed a Bi-Encoder and Poly-Encoder model for response selection, which perform well compared to other baselines and models. That's all. Thank you.
Awesome. Thank you so much, Shane, for that talk. Unfortunately, we will not be able to take questions. In the interest of time, please feel free to direct your questions to Jiang after the session. Thank you. Next, we have a talk by Matteo, Senese, Giuseppe, Rizzo, Alberto, Benincasa, Barbara, Caputo on a response retrieval approach for dialogue using a multi-attentive transformer. Is Matteo in the crowd, or are we? Okay, we're going to play a video.
I'm going to play the video.
Yeah, thank you. I don't think we are hearing the audio though.
Sent our submission for the Dialogue System Technology Challenge number 9.
Can you hear it now?
Yes,
I
it works now.
am Matteo Senese, and in this talk I will present a response retrieval approach for dialogue using a multi-attentive transformer. This is a joint collaboration between the Linux Foundation and the Polytechnic University of Turin, and it represents our submission for the Dialogue System Technology Challenge number 9. The authors of this work are Matteo Senese, Alberto Benincasa, Barbara Caputo, and Giuseppe Rizzo. The task we address in this work is called response retrieval. That is, retrieving the most appropriate answer from a pool of given candidates, this in a dialogue scenario. Here we reported an example of the scenario we faced, where we have an AI agent at the center of the picture that receives a request from the user in natural language. In particular, this user is asking if the skirt is referring to is available also in red. Together with this request, our AI agent also receives the ID of the item. Thanks to this information, it can access a catalog in order to fetch all the information available for the referred item. Using this information, then, the final goal of this agent is to retrieve the most accurate answer from a pool of given candidates. For the sake of this work, the catalog is a structured way to store information about items, and where each item is represented by a series of attributes, and we can assume that the catalog contains all the items the user can refer to in the conversation. In turn, each attribute is composed of the name of the attribute and a list of values. Here, for instance, we have an example where we have a catalog with two different items. The items are represented by their ID, so item 241, item 242, and a series of attributes. For instance, the item 241 has a colors attribute, where colors is the name of the attribute, assuming value red and brown. Thus, the item number 241 represents a skirt available in red and brown by the brand Alborz. Different items can have different attributes, and some item can have missing attribute. For instance, here, the item 242, for the item 242, we do not have any information about the brand. The final goal of our work is to find a good parameterization for our function in order to maximize the score of the true answer inside the candidate pool, given the request of the user made in natural language and information about the item as a list of attributes for that item. To do so, we used a multi-attentive architecture. This architecture is a transformer-based architecture that allows us to constrain the retrieval of the court answer on the user request and the item information. The constraints on these two components are made by using attention mechanisms. So we have the first attention mechanism that compute the attention among the words inside the answer and information about the user request, and the second attention mechanism that compute this attention between the answer and the information about the item, thus being a multi-attentive paradigm. Concerning the scoring criteria, we think that a good scoring criteria should take into account different properties the agent answer should have. In this work, we highlight two different contributions. The first contribution is what we call the log likelihood score. This score takes into account the semantic similarity that should exist between the user request and the agent answer. For instance, if the user is asking about the available colors, the final answer must be related to the colors of an item. Additionally, during inference time, we also used what we refer to as grounding score. This score is used in order to increase the score for all the answer that contains the information specific to the referred item. Finally, the score given to each candidate Y inside the pool will be equal to the sum of the score of the log likelihood score for that answer and the grounding score for that answer. Concerning the log likelihood score, in order to define it, we consider an answer inside the pool, here referred as yi, as a list of words from 1 to m, where m is the length of our candidate. Then, by using our model, we computed the log likelihood of each word inside that answer, based on the user request, the item information, and the entire left context for that word. So all the words from 1 to I minus 1. Then we formulated the log likelihood score as the normalized sum of all the log likelihood for each word inside the answer candidate. The normalization factor is used in order to avoid biases toward shorter answers. At inference time, we also use a grounding score. This score is defined as the recall of the item attributes within the answer we are analyzing. Practically speaking, we use a regex-based approach in order to find all the occurrences of the item attributes within the candidate answer. In this slide, we have an example of how to compute the grounding score. In this example, we have an AI agent that receives a request from the user together with the item ID and has available information for that item inside the catalog. The candidate pool instead is composed of 3 different answers. For the first answer, the grounding score is equal to 0 since it does not contain any information fetched from the catalog. The second candidate instead received 0.25 points since it contains exactly 1 out of 4 attributes from the catalog. Finally, the third and last answer get 0.75 points since it contains 3 out of 4 different attributes for that item. The architecture we choose is a sequence-to-sequence transformer composed of 3 main building blocks. The first component is the encoder for the user request. The second component is the encoder to encode the information about the item that are the list of attributes available inside the catalog. And finally, we have a decoder that produces, condition on the item information and user request, the log likelihood for each word inside the candidate we are analyzing. Regarding the encoder for the user request, this is produced by stacking together 12 different transformer encoders. The input to this module is the string of the user request made in natural language, and the final output is a set of contextual embeddings for that user request. Each embedding is referring to a word inside the user request. For the item encoder instead, we have the same architecture, so 12 stacked transformer encoders, but this time the input is different. We compute the input for the item encoder by concatenating together all the information available inside the catalog for the item the user was referring to. In particular, we use a fixed pattern in order to concatenate all this information, where the name of the attribute is followed by a column and then a comma-separated values for that attribute. The final result of this encoder is to produce a set of contextual embeddings in order to encode all the information available for that particular item inside the catalog. During training, we initialize these 2 encoders with the bare pre-trained weights in order to start with an already good local minimum. Finally, our decoder, here presented at training time, is composed of several attention layers. At training time, it receives as input only the true answer from the candidate pool, and it is trained in order to generate the answer shifted by 1 position. This answer has to be generated based on 3 attention mechanisms. The first attention mechanism is the multi-head self-attention. That is the typical one present inside a transformer. This multi-head self-attention computes the self-attention among all the words inside the answer. Then we have a multi-head utterance attention in order to compute the attention between the answer as input, and the user request encoded by the user request encoder. Finally, we have a last attention mechanism to compute the attention between the answer and the item information. These two additional attention mechanisms, the multi-head utterance and multi-head item attention, are used in order to constrain the generation of the answer on the user request and on the item information. During training, as we already told, we fed to our model, to the decoder, only the true answer. Thus, we are trying to minimize the negative log likelihood of the ground truth answer only, given the user request and the item information. This approach makes our training independent from the size of the candidates pool, thus being more scalable. We used for training the cross-entropy loss and add-on optimizer with a batch size of 256 and a learning rate of 10 to the minus 3. We train our model for 3,000 steps. A difference, we slightly changed how we fed the input to our decoder. This because at different time, what we need to do is to score each answer inside the pool. Thus, we fed the answer one by one to our decoder, and for each of them, we compute the log likelihood of each word. Then, by computing the normalized sum of the log likelihoods, we compute the log likelihood score, and then we sum also the ground score using the Rajen-based approach. Finally, we obtain a list of scores, one for each answer in the pool, and then we sort this list based on the descending order of the score. In this list, the first entry will represent the answer our agent has retrieved from the pool. In order to evaluate the effectiveness of our approach, we used the fashion domain dataset of track number 4. Track number 4 it's called SIMMC, which stands for Situated and Interactive Multimodal Conversation, and it contains a collection of various multi-turn conversations in a shopping scenario. Additionally, the dataset also introduced the concept of metadata attached to each conversation that can be interpreted as our catalog. On this track, on track number 4, we choose the response retrieval subtask, which consists of retrieving the most appropriate answer from a pool of 100 different answers for each user request. The metric defined by the users are the mean rank, the mean reciprocal rank, and then the recalls at 1, 5, and 10. First, we want to understand the effectiveness of introducing the ground score other than the log likelihood score. To do so, we reported here in this slide the results of our model with and without the ground score on the test development split of SIMMC. As you can see, the ground score here reported in the last row improved the performance on the response retrieval task by 0.5 points on the mean rank, up to 2.1% on the recorded one. After proving the effectiveness of the ground score, we computed the results, the final results for the challenge on the official split used to make the leaderboard. This split is the test standard split, and here you can see the result of our model in the last row with the ground score. Our model achieved the second best score on all the metrics defined by the organizer. So, to conclude, in this presentation, we proposed our solution for the response retrieval task at track number 4, in particular on SIMMC fashion dataset at Dialog System Technology Challenge number 9. We prove that our solution is independent from the size of the candidate pool during training, since it is trained only to generate the true answer from the candidate. And we prove that our model achieves good performance by achieving the second best score on all the metrics defined by the authors on the response retrieval subtask. That's all. Thanks for your attention.
Thank you. Is Matteo in the group? I don't think so. Okay. So feel free to forward any questions that you have to Matteo. We'll move to the next talk, which is by Eunjoon, Sejun Lee, Eunjoon Ko, Jung Sion. It's TOM, end-to-end task-oriented multimodal dialogue system with GPT-2.
Hi, I'm Young-hoon. I'm a researcher at Sogang University, Seoul, Korea. Today, I'm glad to talk about TOM, the end-to-end task-oriented multimodal dialogue system with GPT-2. There were 3 subtasks at DSTC9 track 4: structure API call prediction, response generation, and dialogue state tracking. Me and my teammates have participated on all 3 subtasks, and our team ranked first place on the response generation and dialogue state tracking task, and ranked second place on the response retrieval task. For a quick recap, let me explain the 3 subtasks in detail. Task 1 is a structure API call prediction, which uses dialogue history, multimodal context, and the current user utterance to predict the assistant actions through API calls along with the necessary arguments. For furniture domain, there are 7 possible API calls. For fashion domain, there are 5 possible API calls. This task is to choose one API call that the agent should make in order to assist the user in buying the right furniture or clothes. Next, task 2 is response generation task, which uses the dialogue history, multimodal context, the ground truth assistant API call, and the current user utterance to generate the assistant response. As illustrated in this picture, the model encodes the user utterance history and uses multimodal context to understand that user wants to see the back of the furniture. Therefore, the response generator should make a realistic assistant response. This is how the back looks like. It has a solid brown color with a foam fitting. Task 3 is to predict the dialogue act labels using the dialogue history, multimodal context, and the current user utterance. Dialogue act label consists of intents and slots. For example, the user utterance, "I want to buy some chairs," is annotated with a dialogue act, "request get chair," to indicate the user's intent. Before we dive into the details, let me briefly summarize our model, TOM. We first modified the baseline architecture of subtask 3, which was simple fine-tuning pipeline of GPT-2. It was originally designed to perform dialogue state tracking, but we modified it to perform all 3 subtasks. Then we used fine-grained tokenization to reduce the number of special tokens for better performance. Finally, we assembled multiple models during generation to boost up the performance and to prevent overfitting. So let's talk about each methodologies in detail. The novelty of TOM architecture lies in its ability to generate outputs for 3 different subtasks with a single GPT-2 model. The baseline model uses 2 different architectures. One is the LSTM model for subtask 1 and 2. The other is GPT-2 model for subtask 3. The main limitation of the original LSTM baseline model was that it requires different pre-processing, training, and output generation steps for each subtask. We were able to achieve promising results of all subtasks by fine-tuning a GPT-2 model that sequentially generates outputs for each subtask, as shown in this figure. The intuition behind choosing this architecture is that since SIMMC dataset uses multimodal context such as items type, color, or position into a textual form using semantic annotation, we believe that GPT-2 model is capable of capturing this information to enrich its output. The Tom model uses only simple text with domain-specific tokens as inputs. A new pre-processing method is applied to create a single stream of raw text that contains belief state, system response, and system API call for each dialogue turn, respectively. Transformer architecture is capable of learning new token embeddings during the fine-tuning step. Hence, we trained the GPT-2 model with task-oriented specific tokens to mark the end of belief state, EOB, end of response, EOR, and end of system API call, EOS. The proposed model achieved improved performance in all three subtasks when compared to the baseline model, and training different models for each subtask is not required. But because of this nature, we were not able to use a classification model for subtask 2B, which is response retrieval task. Instead, we compare the cosine similarity of each candidate with model-generated responses and chose the candidate with the highest similarity. We used simple one-hot encoding method to represent each sentences and to calculate the cosine similarity. This additional step was done after the model inference time, so it didn't make the training time slower. The second method we took was fine-grained tokenization. Tom model separates primary components of the dialogue act into individual tokens. For example, the belief state DA inform refine furniture is divided into DA, inform, refine, and furniture. They were lowercase to use pre-trained information about the word itself. In the baseline model, 389 and 579 additional special tokens were added to the GPT-2 tokenizer to tokenize each dialogue act into word tokens for furniture and fashion. On the other hand, the Tom model uses only 250 and 367 additional tokens for furniture and fashion domain. Because of this fine-grained tokenization, there are fewer special token types added to the vocabulary. Additionally, after the model generates the output sequence, a post-processing step to concatenate the separated tokens is required for it to be evaluated using the evaluation script provided by the organizers. We trained multiple models with the size variation in GPT-2 models and size variation in the training dataset. During inference time, we assembled multiple models to generate the output sequence. Assembling distinctive models was accomplished by averaging the log probability at each time step and then selecting the word with the maximum log probability. We have done numerous experiments with variation in different hyperparameters. Our finding was that adding warm-up steps to the learning rate and using beam search during generation helps to improve the performance the most. It is because beam search keeps track of several most likely candidates at each time step decreasing the chance of missing hidden high probability word sequences. We used a beam size of 2. This table shows the difference of average performance of each model and the ensemble model. Model 1 is a GPT-2 small model trained with 4.4 thousand dialogues. Model 2 is GPT-2 large model with 3.8 thousand dialogues. And Model 3 is GPT-2 large model with 4.4 thousand dialogues. And at the last row, there's a score of an ensemble model of these 3 models. We can find that the ensemble model increased performance in almost every metrics. This is the final result of our model with the test standard data. We compared our average test standard score of furniture and fashion domain with the score of the runner-up model and the baseline model. Our interpretation is that because our model can learn various information before it generates the response, it has higher blue score compared to the other architectures. Here are some examples of response generated from the baseline model and our Tom model. It is from the training dataset. In this dialogue, the user's utterance is, "That looks a little too light for what I need. Do you have something else with a high customer rating?" The ground truth response for this utterance is this one is the highest rated at 4.84. The response generated by the baseline model is, "This is also a pattern sweater. Would you like more information about it?" It is pretty far off because the assistant does not even talk about the customer rating, but chooses to talk about the style of the clothing. Meanwhile, the response generated by our model, this has a rating of 4.42. What do you think? Looks much more appropriate. Moving on to the second term in the same dialogue, in response to the user's utterance, who designs it? The baseline model and the Tom model both fail to generate the correct response. The real answer is, "This is made by Fancy Nails," but they both stated the wrong brands. However, it is interesting to see that the response generated by Tom model is more detailed, as it specifically states the item as sweater. This sweater is from New Fashion. We believe that this shows that Tom model is better putting the multimodal context into consideration when generating the response, making the response more specific and realistic. This is the end of our presentation. Thank you for listening, and feel free to ask any questions. Thank you.
Thank you so much. Do we have Jung in the audience?
I believe he's there.
Yes.
Oh, okay. Awesome. Feel free to ask any questions to the authors.
So I have a question. So you mentioned that you kind of break the dialog act tokens down into kind of finer grained tokenization. I didn't, unless I missed it, I didn't see what win you thought you got from that or what gain you thought you got from that. So I'm just interested, how much of a boost did that give you?
So the question was that what was the intuition behind doing the fine tokenization before training the model? So it was basically with the idea that so the dialogue acts are composed into multiple vocabularies, like such as ask questions or like what's the color of the furniture or fashion or this clothes. So we thought that if we parse those components into the vocab that GPT-2 have already seen when pre-training, during pre-training, it can more efficiently get the information behind that those dialogue state acts while fine-tuning process. So that was our intuition behind that fine-tuning tokenization.
And did you measure with and without that fine tuning?
Yes, we did. And it had, we didn't put the experiment results at the presentation, but we found that it had a increase in the overall performance with dialogue state task, dialogue state tracking task.
Okay, cool. Thank you.
Thank you for your question.
Yeah, thank you for the wonderful talk. I have a follow-up question to what Paul was asking. So at prediction time, how did you handle the model predicted dialogue acts if you split all of the dialogues acts into individual tokens?
Okay. So the question was that by using that fine-grained tokenization, how did we make it into the real token after model inference time? So what we did, we added additional post-processing process to capture the tokenized tokens. So like it should be divided into 4 components like DA, ask, like request, furniture. So we capture those sequence and then concatenate that parsed sequence into the original form to evaluate the result.
Got it. Did you find that when you concatenate, the resultant dialogue act is invalid, or did you always find it to be valid?
We found that it contained the original form, and we found that it was valid. Thank you for the question.
Thank you.
I have a question. So out of the 3 improvements that you talked about, which one gave the largest gain? So like you have one on ensembling, one on tokenization, and another one, I'm forgetting what was it. So out of these 3, which one is giving you the best like improvement?
So the question was that among 3 methodologies, which one had the most performance boost? Yeah. So, okay, it's a great question. So the most performance gain we had was the methodology 3, which was a ensembling and beam search file generation. So while like doing numerous experiments, we found that using beam search and like doing the generation with and without beam search had a much difference in the performance. And also like doing ensembling multiple models helped the model to generate more general responses.
So when you have ensembling with beam search, that would be like very expensive, right? Because you generate the samples and then you need to sort of like if your beam size is 3 and your ensemble size is also 3, then total of 9 combinations probably.
So you mean the trade-off between like inference time and model size, etc.?
So like if you combine ensembling with beam search, does it like blow up in some way computationally?
It indeed takes more time, while inference time, than just using a single model and using a beam size of 1. So we had to like have that trade-off between performance and inference time.
Yeah, thank you.
You're welcome.
I'm just wondering whether I could actually ask a question about the first paper, seeing we didn't have time. Yeah, hi, Jung.
Yeah.
So I noticed in your presentation that there seemed to be a big, like 4 to 5 point jump going from something which was like MTN or simple Todd, so kind of GPT-2 class models, to BERT class models in one of the tables you presented. And I just wondered what you thought gave you such a big jump in moving between the classes of models.
I think because because first of all, for the MTN model, it's actually not a pre-trained model, even though it's performing well for the multimodal dialogue data, including the visual information and the text information, but actually it's not a pre-trained model. So that's why the pre-trained model are much better. But if, let's say, the MTN can be pre-trained, it's that if we have the time to pre-train the MTN and to do the comparison, the result might be interesting to compare. Another reason is we are actually following the latest paper. I think it's a bird-to-bird paper talking about different variations of pre-trained encoder-decoder structures. And actually, I think that paper also experiments some text generation tasks, which achieves reasonably well in some tasks. So we also try with this kind of approach for the dialogue generation, because we consider them as a text generation. And also we find out the models like BART or bird-to-bird or bird-to-GPT2 is performing generally better in terms of text generation. So I think it's possible that the bird-to-bird or the BART is also performing well in other text generation datasets compared to the single GPT-2.
Thank you.
Thank you. Is there any other questions?
Hi, I want to ask the further question for the third paper.
Okay.
When you're doing the GPT-2, because you definitely need to do it in autoregressive way, but for the state tracking task, sometimes you need to have the slot and value, a lot of pair of slot and value, but the order of the slot value pair may not that important, right? Because you can have like random order for this set of the value, this set of the slot value pair. So do you think about for example, you can randomly shuffle the data for the pairs and try to do it, or just slightly modify the architecture to make it not non-autoregressive way?
I'm not sure if I understand your question correctly.
And let me rephrase it again. Because during the state tracking stage, you need to predict the first slot and the value. And then based on this information, you predict the next slot and next value, right? Yes. Which is the auto-regressive fashion. But actually, they may not be that order. You can generate the second slot first, and then the first slot.
Mm-hmm.
So did you consider to, for example, you can mask the input, not allow the original auto-regressive scenario, or try to see whether the performance will be improved or a drop?
Oh, we did took that into consideration, but since we didn't have like enough time to do various experiments, I think we haven't tried that method to compare the result. But I think it's pretty interesting idea, and we will look forward to try that and see the results different in the future.
I see. Okay, thank you.
Thank you for your comment.
Awesome. I think we are almost at time. Unless there are any other further questions, we can wrap this session. And then please, if you have any further questions, please write to the, feel free to write to the corresponding authors for any additional clarification. Thank you.